Alright, so today we're going to talk about thermochemical equations, and we're going to do a little bit of stoichiometry with that. Nothing too new, just plugging in a different number, kind of like we did with the gases. So here's the note sheet that you will want in front of you, and we'll kind of fill this in, and there are a few examples that we'll do with this, so make sure you have everything here in front of you. As far as homework, I'll get to that at the end. Let's go ahead and go through the notes and the examples first. So, for thermochemical equations, here's what we want to think about. First of all, thermochemical, okay, an equation. We have a chemical equation, and there's some thermal things going on there. So thermal meaning like heat being absorbed or heat being released. So Tuesday we talked about exothermic and endothermic equations and reactions. So exothermic meant we release heat overall, and endothermic means we absorb heat overall by the time everything's said and done. So here's the main idea we want to think about. If I have, and you don't have to write this down, but if I have the combustion of hydrogen gas and oxygen gas, that'll form water. And combustion means I'm basically igniting these two things together and I end up getting water. And this reaction's exothermic. So my delta H for the reaction is a negative 241.8. So that's how much heat is given off. And then what we want to think about in this section is, well, what if I double the amount of hydrogen and oxygen that I react together or that I combust? What will happen to the heat given off? The answer here is that basically the heat will double because you have double the amount of stuff you're reacting, and a certain set perfect amount will give off this much, and just if we double the amount of substances, the more things reacting, the more bonds breaking and reforming, will double the heat that we output or produce in this case. So that's what we're going to look at. We'll look at some chemical equations where we're doubling and tripling things and seeing what happens to the heat. So we'll use that idea. Okay, so here's the first part of your notes, and it's kind of what I just said. Basically, the energy given off by a reaction will depend on how much of the substance is present. And we call an equation that represents heat change a thermochemical equation. So I'll let you go ahead and fill those in. Okay, so we want to look at, we have to make sure we know what states the substances are in. That'll kind of give us a clue of what we're doing with the energy. And we have to kind of make sure we're including how much energy is given off or taken on. Those are kind of the rules of a thermochemical equation. And like any chemical equation, we have to make sure it's balanced. Okay, let's go back to this diagram. This was from when we talked about phase changes. So some of the phase changes we talked about, for example, were deposition and sublimation. So if you have deposition, that's when we go from gas to solid, so like the frost on your windshield in the winter that you have to scrape off. That released energy because I was reforming some of those particles from gas to solid, so I gave energy off to do that. So that would be an exothermic type of change if I'm releasing energy. Oppositely, if I am going from solid to gas, or sublimation, I know that I am exciting the particles, so I have to absorb energy in order to excite the particles. If I absorb energy, that's an endothermic reaction. So anything going from a really excited state down to something less excited will be exothermic, heat gets given off. Anything going from not very excited like a solid to something slightly more excited like a liquid or very excited like a gas, that will be endothermic. I'm going to take in a bunch, of energy in order to get the change to happen. And that'll be true for all of these other phase changes. So like melting, solid to liquid, that would absorb. Freezing will release. And then for condensation, we're releasing, going from gas to liquid. Vaporization, we're absorbing. Okay. So again, absorbing means endothermic, releasing means exothermic. All right, so what do we have to do with the math and the numbers? Basically, for each type of change there's a certain amount of energy, or we refer to that now as enthalpy change, and we get a delta H. And basically, these little abbreviations here, so if you see COMB, VAP, and FUS, essentially that's just a label for what type of change we're doing. Really, what we care about is the number we get with these delta H's. That's what we need to use to calculate stuff. So I'll let you guys go ahead and fill this in. I'll kind of talk about it. All right, delta H COMB, if I'm combusting something, that means the reaction will have some substance that's combined with CO2. So if you're looking at a chemical equation and you notice you're reacting something with O2, that's going to be combustion. And that's just the enthalpy change or the energy change we get when we burn something, basically. And for us specifically, that's going to be 1 mole of the substance. If I'm burning something, I'm giving off heat from the flame, so that will be an exothermic reaction. So this delta H COMB will be negative. Okay. Likewise, for these two, we have a phase change. So if I vaporize something, that's what the VAP stands for. The formal word for this symbol is molar enthalpy of vaporization. So basically, the energy required to vaporize 1 mole of a liquid. And this would be from liquid to gas if I'm vaporizing, just like we had in the previous slide where we had the chart. So this number should always be positive because we are vaporizing and taking on energy. Delta H fusion, or FUS, molar enthalpy of fusion, basically means if you're melting something, that's the energy required to do that. So that would be a solid to liquid phase change, and that number should be positive because you're absorbing energy to melt. Okay, these are always carried out under standard conditions, which basically just means 298 degrees Kelvin, which is about 25 degrees Celsius, and 1 atmosphere of pressure. And here's some examples. If I am, what's happening to the energy? So if I'm doing vaporization, HVAP, energy is going up. Okay, same thing with fusion. I could also have a delta H for sublimation, which would be really big energy change from solid to gas, but we'll deal mainly with HVAP and H fusion. 2 other numbers we get, obviously there's more phase changes we can do, so here I have delta H for condensation and delta H for solidification or freezing something. So I'll let you go ahead and fill those in. All right, so delta H of condensation, again, means the enthalpy or energy required to condense something. So when we condense, we go from gas to liquid. And if we're going from gas to liquid, we're going from being really excited to not as excited. So we're releasing energy, meaning this value should be a negative number. Here, I'm going to have, as far as what type of negative number, if I vaporize something, I know that's kind of the opposite of this, going from liquid to gas, which was a positive number. Condensing something is going the opposite direction. So numerically, if you want to know delta H condensation, you have to know the delta H of the opposite, which is vaporization. And then they just have opposite signs. So like delta H of vaporization was positive, condensation is the same numerical number, just the opposite sign of that. Same thing with delta H of the solid or freezing something, the amount of energy it takes to freeze something, so liquid to solid. That was the opposite reaction of something going from solid to liquid or melting. So they'll have opposite signs. Delta H of fusion meant that's the heat for the melting, that's the symbol we need. That'll be the same numerical number, just a different sign. And we'll look at an example of that. All right, so what do we have to make sure we know? We have to make sure we're given an enthalpy value or given enough information to find one. we have to make sure we know the grams of one of our products, and then we have to make sure the equation is balanced. One thing you'll want to remember is the reverse reaction for something will have the opposite for delta H. So if you know delta H of one reaction, if you basically flip it around, instead of maybe producing water, you start with water instead, the delta H number is the same, it just has the opposite sign. So if the one direction for the reaction was positive, the reverse direction is the negative of that number for delta H. All right, so let's go ahead and look at our first example. So these will look fairly similar to the stoichiometry problems we've done. We're just making sure that we incorporate delta H, or we're incorporating energy, because thermochemical equations have to incorporate energy. So here we have an H, delta H of COMB, which meant combustion. And that'll kind of be noted in the problem that you're combusting something. So it tells us that that H, delta H value is negative 113.67. Or sorry, 1,367. There we go. All right, how much heat is released from this particular reaction when 82.1 grams of carbon dioxide is produced? So I know I have a gram number. That's what I need. I need something in grams or at least moles, but usually we'll get it in grams. How much carbon dioxide, or how much energy is given off when I have this much carbon dioxide? So this is what I'm starting with, and here's the piece of information I need to incorporate. So first thing that we've always done with stoichiometry, if you've got grams, you have to keep calm and convert to moles. So the first thing we want to do anywhere is get the 82.1 grams of CO2, carbon dioxide, into moles of carbon dioxide. So if grams start here on the top, I don't want grams, so they're going to go on the bottom. Moles go on top. And hopefully you remember what number goes down here, and I'm not there to hear you say it or mumble it under your breath, but it should be the molar mass of CO2, which is about 44 grams. Okay? So that first step will get you to moles. Second step we have to think about is the heat part in this case. So if I'm starting with grams and I want to know how much heat, it depends on how many grams there are. The more grams I have of something, the more heat I'll produce. So let's take a look. Here I have 82 grams, and then the molar mass of like 1 mole of this stuff is 44. I have almost double, a little less than double 44 grams. So really what should happen is I should end up kind of doubling the heat value, hopefully. So let's go ahead and take a look. Alright, so now I'm in moles of CO2. So then I need to incorporate heat, so I don't want moles. I want heat, and the unit for heat is kilojoules. And this reaction tells me that there are negative 1,367 kilojoules for this reaction to happen. Now, this isn't per 1 mole. This is specifically for this reaction, and this balanced equation tells me that I have to have 2 moles of CO2. So when you do the heat part, you have to make sure you're looking at the recipe, because the amount of heat produced depends on what is there. So in this recipe, it's saying if there are 2 moles of this stuff there, this is how much I'll give off or produce. So here, let's take a look. Well, these are always going to be 2 steps. First step is typically get it into moles if it isn't already. Some of them may be given in moles. I think it was nice a few times on your homework. And then the next step is accounting for heat. Just make sure that this number is coming from the equation. That's going to relate the heat. So here we'll take 82.1, multiply across, times 1, times negative 1,367, divided by the stuff on the bottom, multiplied together. Okay, and then you'll get a number for that. We'll go ahead and go to the next video. I'll let you guys plug and chug this, and you should get an answer. And we'll go ahead and move on to the next example in the next video.